progress. Everything is ready to go. Okay. So we're pleased to have Zebrowski here from University of Chicago. She got her PhD from Berkeley in 2022, and then had not one, not two, but three postdocs at Chicago and Fermi Lab. The first was a Nighttime Fellowship until about 3 months ago, and now she's a Letterman Fellow and a KIPC Fellow. It's a joint appointment, and excitingly, she was appointed to become an assistant professor at University of Chicago starting in July, right?
July, yeah.
So she's an expert, not only with flight intensity mapping, but general cosmological instrumentation and analysis. And today we're here to talk about intensity mapping. So take it away.
Great. Thank you for this warm welcome, everyone. I'm so happy to be hosting bingo on your I hear there are bingo cards going around, and I will say that if anyone wants to yell bingo in the middle of my talk, you are welcome to. I will welcome that. But yeah, it's great to be visiting my Southern Illinois neighbors. Always a pleasure to be at U of I, and I've had really wonderful talks today, both from the various faculty members of the department, but especially the grad students. Thank you all for coming out to have lunch with me, and lots of good conversations. So without further ado, today I'm going to be talking to you about line intensity mapping. So a new window into the high-redshift universe with line intensity mapping. So in my mind, the perfect place to start a cosmology talk is with the Hubble Deep Field. So the Hubble Deep Field is where they took the Hubble Space Telescope and pointed it at a region of space they thought was completely empty. And obviously, as you can see, it is not completely empty. And this image really just reminds me, it's one of the first images I saw that just struck me with the vastness and richness of the structure of our universe. And it's a picture that really wants to make you understand the underlying rules that govern its evolution. Now, one person who famously had similar thoughts and made some measurements was Edwin Hubble. And as you can see in the top right, he made this very famous measurement, which is the greater the distance between a galaxy and Earth, the greater its recessional velocity. And from this measurement, you can infer one of two things. So the first is that the Earth is the center of the universe and everything is moving away from it, or that the universe is expanding. So once faced with this proposition that the universe is expanding, the natural inclination is to then turn the clock backwards, which implies that at one time, the universe was at a much smaller, hotter, and denser state. And scientists have built a model of cosmology around this simple paradigm that the universe began in a hot, dense state and then subsequently expanded and cooled off. Now, as an experimental cosmologist, to understand if this idea about the universe's history is correct, I build telescopes. And here you see some of the information that we have about our universe from other telescopes that have been built. So at the beginning here, at the cosmic microwave background, you have an image given you by the Planck satellite. And of course, you have the Hubble Deep Field made by the Hubble Space Telescope. But even with just these two slices in time in the history of our universe, we can start to see that this simple picture of smaller and denser and then expanding and cooling doesn't line up. So for example, in measurements of the cosmic microwave background, the oldest light in the universe, we measure this striking isotropy, which implies a homogeneity of causally disconnected regions of space. Now, some call this the horizon problem. And this is super paradoxical because how do these regions that had never been in causal contact know to be the same temperature? Another paradox you can see with your own eyes is, why do you see structure? What led to the formation of all of the structure in the sky? And these and many other questions have puzzled scientists, and we posited this theory to explain it called inflation. And this idea that we live in an inflationary universe has led to the history of the cosmos that most scientists believe to be true today. So let's start by going through, this is the free space on your bingo card, right? Going through a history of the observable universe. So on the left here, we have the Big Bang, the hot, dense point of the universe beginning. And right after that, we have inflation, this superluminal expansion of the universe, a faster than the speed of light expansion of the universe. So this solves causal contact because regions were in causal contact before then. And this answers the question of why we see structure, because this stretches these quantum random fluctuations in the early universe to seed structure. But inflation is actually this extremely mystifying event. It was super, super energetic, an energy scale of something like 10 to the 16 GeV, and it doesn't fit in with anything else that we see in the standard model or have seen since in our universe's history. But it does make these problems make sense. After this, we had a hot plasma expanding and cooling until the first subatomic particles form, until finally the first neutral atoms form, allowing photons to free stream through the universe for the first time. And this is what we refer to, and many of you in this room study, the cosmic microwave background. After that, we have the cosmic dark ages. So this is before stars, when hydrogen filled the universe. And then we have the formation of structure. So I like to see this little image of the formation of large scale structure that I think really helps me understand why we get this. So you have the sea of hydrogen, but there are these quantum fluctuations from inflation, and under gravity, the overdense parts collapse, and you start to get stars and galaxies and all of the familiar structure we see today. So this is a very nice picture of the history of our universe, but there are still these huge unsolved mysteries that we have. So for example, what mechanism drove inflation? What is dark energy? And how did the first stars and galaxies form? And what's kind of interesting is that when we think about the information that we know about the history of the universe, most of the information is coming from the endpoints in cosmic history. So we have great pictures of the cosmic microwave background from telescopes like SPT and BICEP or the Simons Observatory. We get a wonderful picture of our local universe from galaxy surveys such as Rubin or DESI. But these are mostly the endpoints. And as good scientists, we know that with 2 points, you can draw a line. But if you have a measurement in the middle, you can see if things are changing over time. And that's why I've so recently been getting interested into this new field of line intensity mapping, which can bridge the gap between the CMB and now to try to fill in and make measurements of some of these middle years of cosmic history to hopefully solve some of the big questions that we have. So line intensity mapping uses emission from atomic and molecular spectral lines from galaxies, things like CO, C2, hydrogen, etc. And this maps the 3D galaxy distribution. This sounds great. Obviously, there's a catch. So the first catch for this is a cosmological probe, is that you need many, many detectors on the sky to measure and make cosmological constraints. And the second catch here is a double-edged sword. So this is a really young field. So no competitive cosmological constraints have been measured yet, but that's also why it's so exciting to be getting into. So what is this measurement? What you measure is a low resolution intensity map of atomic or molecular spectral line emission, and you measure it at multiple frequencies. And what this traces, as you can see, if you can line up the dots in the emission patterns up here, is the large scale structure in the underlying galaxy population, which in turn obviously traces the dark matter distribution as it evolves over time as the spectral line redshifts. Now, this is super complementary to the CMB. So the CMB is the surface of last scattering, as we call it. This is only one cosmological epoch. But with line intensity mapping, you get this cube of data. So you get a lot more modes. This is also really great for constraining cosmological parameters because it breaks degeneracies in the CMB. However, for those of us who are in line intensity mapping now and come from a cosmology background, you can use the same intuition you had for cosmology analysis and borrow a lot of the data analysis techniques that we have from the field of CMB. It's super synergistic. This is also really complementary with optical galaxy surveys. So this is a fundamentally different tracer, cold gas versus optical light. So you're already learning something new. But the thing that's cool about line intensity mapping is you have this potential for higher redshift. So with galaxy surveys, you have galaxies until about redshift 2 or so, then you can go with quasars until redshift 4. But with line intensity mapping, you hopefully can go back all the way in time as far as, for example, carbon monoxide has been emitted. The other thing that's different about optical galaxy surveys versus line intensity mapping is that with optical galaxy surveys, you take your little robots and you go point at one galaxy and you observe it. Then you observe the next galaxy. Then you observe the next galaxy. Whereas with line intensity mapping, you are making these maps, doing a field survey of the sky. So you're getting all of the integrated emission, as opposed to just getting the brightest points of this distribution. But obviously, this will be super powerful in cross correlation, especially with these first line intensity mapping data sets. The third thing that's, I think, hopefully evidence to you all as well, is that there's a big multi-line complementarity in doing line intensity mapping with multiple lines. So each atomic species reflects different properties of the host galaxies. So for example, if you look at this galaxy distribution at the top and how that looks in a 21 centimeter versus CO line intensity map, if you have many galaxies that ionize the IgM, and this looks like a hole in the 21 centimeter map. Whereas if you have many galaxies, this causes star formation and produces metals, which is a bright spot in the CO map. So by taking these two maps, you can see the interplay of them and understand the physics of what's going on. The other thing that's really nice is that these line intensity maps span many frequencies in terms of instrumentation systematics. So if you're looking at the same patch of sky in 21 centimeter versus CO, they don't have overlapping instrumentation systematics. And obviously, this will be super powerful in cross-correlating many line intensity mapping data sets. And so what I hope to impress upon you is that line intensity mapping is this truly new window into our universe's history, spanning back from now all the way, hopefully, until cosmic dawn. And over the next few slides, I'm going to tell you some of the promise, some of the scientific promise that I hope that this holds. But every time that we've opened a new window into the history of our universe, the universe has surprised us. And what I'm really hoping is that the most exciting thing that comes from this new field is something that I haven't even thought of yet today. So with line intensity mapping, you can constrain the astrophysics of the high-redshift universe. Now, recently, we've been getting some big surprises with these high-redshift galaxies, as have been observed by JWST. And you may have seen the headlines in the paper that JWST has, in fact, broken cosmology. Now, I do not know if that is true, but I do know that astronomers are puzzled. And what I'm hoping is that with line intensity mapping, we get this integrated map of CO or C2, this cold gas as a function of redshift. And this can help us get a handle on galaxy formation and evolution. And what this is cool for is that this is one of the only near-term and importantly super cheap ways to probe the cold gas phase of the ISM going back in cosmic history. And so get this really unique handle on the star formation history of the universe. But you can also constrain cosmology. So for example, here I've plotted the Hubble tension as a function of redshift. So I've put the different values of the Hubble constant on this plot, basically where they're measured in the universe's history. And you can see the commonly known thing, which is that the early universe versus late universe measurements of the Hubble constant have these small and non-overlapping error bars. And what I think is super interesting is making a measurement of the Hubble constant, an independent measurement somewhere in these middle redshifts, and seeing if it agrees with one of the two endpoints or shows up somewhere in the middle. Obviously, this is also a probe of the expansion history of the universe. So dark energy, this mysterious cause of the universe's accelerating expansion, you can make a map of how dark energy is affecting slices over time, hopefully right when its effect first became important. Additionally, you can constrain inflation. So correlations at the end of inflation are because of physics that are happening during inflation and printing this there. And when we make line intensity mapping maps, we study them via their statistical correlations, but these are actually primordial in nature. And we can name this parameter, which we call FNL, which is a parameter describing the degree of non-Gaussianity we see in these maps. And single field inflation predicts really only FNL less than 1. But if you have multiple field inflation, you can learn from the shape dynamics of the inflationary field or field and of any other particles that may have been interacting with the inflaton at the time. And the really unique thing about line intensity mapping for measuring this non-Gaussianity is you get this large amount of linear modes because of such the huge volume of cosmic time that you are spanning. The last thing I want to highlight is that you can also do particle physics and search for new light particles. So N effective is this number that corresponds to the number of relativistic species in the early universe. So this is sensitive to the number of neutrinos, sterile neutrinos, light dark matter, axions, etc. And this smears out structure within the free screening scale. So in this figure, I'm plotting N effective of 1 versus 10. And if I flip back and forth, you can see how you're seeing this smearing out of structure. And this is something you hopefully will also be able to do with line intensity mapping. So sort of in short here, I think this plot really encapsulates some of my hopes for line intensity mapping as a new cosmological probe. In the legend here, you have a bunch of your favorite cosmological parameters. So the sum of the neutrino masses, neutrinos and light relics, primordial non-Gassianity inflation, dark energy. And the y-axis here is the how good your error bar will be relative to Planck. How many times better than Planck, which is kind of state of the art for a lot of these things. And the x-axis is spectrometer hours, which is kind of funny unit, but it's just saying that if you want a more sensitive telescope, you either integrate for longer, you get more hours, or you add more spectrometers, more detectors on at once. And you can see as you're moving toward the right side of this plot, you're starting to get these pretty solid improvements over what Planck can do. And this mostly comes from this, again, large volume of modes and breaking of parameter degeneracies in CMB data. And this is kind of where I hope the field is heading. So let's talk a little bit about what this measurement is. And to do that, we have to go back to the basics of line emission. So in an atom, electrons can only exist at specific energy levels. So you need to absorb or release photons through transition. Similarly, molecules can only vibrate and rotate at certain rates. So for example, when CO changes its rotational state, it absorbs or emits a photon in the millimeter wavelength. And this leads to what we call the CO rotational ladder. So CO only emits at 115, 230, 345, 461, 576 gigahertz. This is the CO rotational ladder. And in the line intensity mapping community, we might like to make plots like this. So this is the mean line brightness temperature as a function of frequency. And I'm going to show you that you can find the CO rotational ladder on this plot. So for example, if you look at 230 gigahertz, look at the color bar, the rest frame is redshift 0. You can see there at 230 gigahertz is CO21. Likewise, CO32, 345 gigahertz, redshift 0, you can see it on the plot with the red arrow. But if you make a map, at these two frequencies, you're getting rest frame. But if you go a little bit down in frequency, you are now looking back in redshift. So that is why this measurement is you're making these measurements at multiple frequencies. So you trace these lines over time as the line redshifts. So you might ask, all right, I got to get this basic premise of line intensity mapping. Which line should I pick? Here's a bunch of the familiar lines that people who do line intensity mapping talk about: CO, C2, nitrogen, oxygen. In my mind, there's really two places on this plot that make sense to look at. So one is you just say, I'm going to look where it's brightest. I'm going to go for the maximum signal. And if that's the kind of argument that resonates with you, you're looking at CO. You're saying that is the highest point here on the plot. This is making you're now building a telescope in the gigahertz. This is nice because you can do it from the ground because the atmosphere is transparent in gigahertz. Maybe you're looking at that and saying, wow, that is a lot of lines on top of each other. It's going to be really hard to disentangle what line is doing what. So that's the maximum signal point, but that is not the maximum signal to noise. And if you want this maximum signal to noise, then you're someone who wants to make an experiment that looks at C2. So this is a log scale plot. If you take a map of 1000 gigahertz and you take the Fourier transform of it, you're mostly getting C2. You don't have to deal with this whole separation effect as much. And you're looking at the maximum signal to noise. The only catch here is this light blue line. So this light blue line on the plot is atmospheric absorption. And you can see that while it's very, very low in the gigahertz, you have these nice windows that you can look through. As you get into the terahertz, you're getting a really high level of atmospheric absorption. So you're having to now do your experiment from space. Now, I think that, yes.
Yes, so are the curves, so is that the expected intensity over the history of the universe for some reasonable cosmology?
It's the expected intensity at that specific point in redshift. Yeah. And you see these peaks because they're basically tracing star formation. Yeah. So I think that this argument about signal to noise versus signal, both I think are pretty reasonable arguments. So I work on experiments that look at both places. I work on SPT-SLIM, which is a gigahertz experiment that does CO from the ground. And I work on TIM, Terahertz Intensity Mapper, which is a balloon-based telescope looking at C2 from space. And this will kind of, in some way, wrap in what I view as two of the three big challenges for the field of line intensity mapping: the instrumentation challenge, the data analysis challenge, and the epic challenge. So the data analysis challenge is that new techniques need to be developed and perfected for these sensitive instruments. Yes, Gil?
So in that previous plot, where would the continuum be?
Higher than this. It's the continuum isn't plotted on this plot.
That higher,
Yeah.
10 times higher or 100 times higher?
Who those? Yeah. Okay, so other than the continuum, the three big challenges that I see in line intensity mapping are this instrumentation challenge, the data analysis challenge, and the epic challenge. So the instrumentation challenge is, how do we build instruments with the raw sensitivity to make competitive cosmological constraints? And I think when you're in a regime where you're just looking for raw sensitivity, you're trying to eke out the maximum signal. However, we also need to be building new techniques to be developed and perfected for these sensitive instruments, which is this data analysis challenge. And I think that you want to start by solving this data analysis challenge where it's easiest, in the high signal to noise regime. Then there's this epic challenge, which is, how do we look far back in time as possible? And if you're doing that, I think you want to look to hydrogen, to 21 centimeter line intensity mapping. So this will kind of present an outline for the rest of my talk. So first I'll talk about the data analysis challenge in C2 with Tim. Then I'll talk about the instrumentation challenge with SPT-SLIM. And I'll finish with a little bit of an idea that we've been kicking around in Chicago to think about how you can look back as far in time as possible. All right. So any other questions before I start there? All right, let's kick it off. So the Terahertz Intensity Mapper is an Antarctic balloon to map the universe in C2. We have flights, we have flight slot in winter 27-28 for McMurdo Station, Antarctica. And this is a picture of what it looks like to launch an Antarctic balloon, which hopefully will be exactly what we're looking at when we launch in 2 years. And you might ask, why would you do a telescope on a balloon? That's a fair question. And the reason that I like it is because you get a space-like environment. So I like to say that it's 0.3% of the atmosphere for 1% of the cost of a satellite. And that's a pretty good value proposition. So when you launch from McMurdo, you can view the same patch of sky for up to a month flight. So if you look here at the top right, that's a picture of the flight path of Anita 4, which is a previous Antarctic-based balloon. So you kind of circle the South Pole based on how the wings are lined up. And the thing that's cool about balloon-based telescopes is that NASA uses as sort of the technical readiness level pathway to space. So if you eventually want to do something like a line intensity mapping satellite, flying this technology on a balloon and proving that it works on a balloon is a really, really good first step. So before I go any farther, I want to shout out that this is a huge collaboration of people, not just myself, of course. So it's led out of Illinois by our PI Joaquin Vieira and Jeff Filippini. But we also collaborate with Caltech, Arizona State, Arizona, Penn, Max Planck, Harvard, and myself at the University of Chicago. So Tim will have a pencil beam survey like light cone tracing C2 and a volume of 2 by 10 megaparsecs cubed, or for over 4.5 gigayears of evolution across cosmic noon. So this is the peak of star formation. And you can see here in this nice rendering of what the TIM data cube will look like from grad students Evan and Shub. And the cool thing is that we'll be making these, well, the measurement is these slices. So we'll be making a map of the sky, but it'll correspond to a redshift slice of redshift of 0.65, of 1.01, and so on and so forth, until we build up this whole TIM data cube. And even just with this basic data cube, you can already start to do interesting science, just with direct detections. So if you think of these individual lines going through the cube as lines of sight, and you ask yourself, you know, each line is a function of frequency, do any of these pop over the notional threshold of detection? And how many of these do we see? You can already start to constrain the C2 luminosity function. Just by asking how many do we even see in TIM, you can start to roll out different models. But of course, you can do more clever things than just asking how many blobs do we see. And one of the first ones you can do is do a stacking analysis. So if you have a galaxy catalog, you can say, I know where these galaxies are and stack on those locations. You can divide your data cube up into 2 different big redshift bins. You can stack them by star formation rate, and you can derive the average far-hour spectral properties of samples of galaxies. So for example, their metallicity, their star formation roads, their specific star formation rate, and start to understand this evolution by looking at the universe in C2. But you might say to me, well, you know where the galaxies are. Can't you do something more clever than that? And the answer is yes, so you can do a cross power spectrum. So in this forecast from Justin Brax, you can see that if you cross correlate with the AstroTeeth catalog, you can start to get this constraint on the power spectrum. If each one of our 4 redshift bits, we should be getting a signal to noise ratio of greater than 10 in cross correlation. And this paper was just on the archive actually last week, so I'd encourage you guys to go check it out if you're interested in this kind of science. But of course, the heart of line intensity mapping, what we hope to do is do an auto power spectrum, just totally internally to our data. Where you can see in this forecast from Ryan Keenan, you can constrain the C2 luminosity function, which can then be translated into a measurement of the cosmic star formation rate density at cosmic noon. And the thing that I think is cool is, you have this balloon, it's flying around Antarctica. Even if we only get 15 hours of flight, which is a pretty short flight, we're already constraining half of the models of the C2 luminosity function. And if we get 200 hours of flight, we should be able to detect some of these at a pretty decent significance. So this, in my mind, is some of the science that we'll get from Tim. We'll get this direct detection, this stacking, this cross power spectrum, this auto power spectrum. We'll learn about galaxy and star formation from this data set. And this will be this really nice precursor to doing cosmology with line intensity mapping. So if you start thinking about the instrument, TIM at a glance, we have a 2-meter primary mirror, about 2 grating spectrometers that go from 240 to 317 microns at about R of 250. We have 2 arrays with 3,600 kinetic inductance detectors. And this is a rough timeline for the project. So we had our test flight 2 summers ago in Fort Sumner. And then next summer, summer after this one, we'll have a hang test in Palestine and a flight from McMurdo, Antarctica right after that. So you might ask, what is a TIM test flight? And this is a NASA milestone to prove communications, drivetrain, and launch readiness. And the golden rule of test flight is that you don't fly anything expensive because this payload is going to crash. So you don't fly your mirror, which is a really expensive mirror, and you don't fly the cryostat. And instead you do, as you can see, our beloved Jay Alameda filling a block filled with concrete to have a mass model, the exact mass of the cryostat instead during test flight. So we began our test flight with an empty hangar in Fort Sumner, New Mexico. This is truly, I would say, in the middle of nowhere, but it's this nice NASA facility that's out there. And it's intended to be remote so that if anything happens with these balloon launches, that you're not hitting a big town. Then we started from this empty hangar building up the gondola. You can see here, leveling the A-frame at the bottom. You can see all of the big structure of the big sun shield being made and all that covered in aluminized mylar. And at the end of about a week and a half or so, we had gotten together this fully assembled gondola for TIM, minus, of course, mirror and scientific experiment. We had our launch on September 23rd, which was our 9th attempt after many, many late nights of getting scrubbed. And here you can see the launch of TIM. It's taking off in this actually really, really beautiful textbook launch. You can see the view down from TIM at the launch train. And if you look up, you see this nice blackness. You can see that the balloon is really looking at space. We had a super successful flight, 4 hours. All of our NASA milestones passed, got cut down right across the border. And I think that this was just super heartening for the future success of our instrument. So there's tons of work here at UIC preparing the cryostat for flight. So I wanted to shout out the UIC cryostat teams. This is Jeff Filippini and Joaquin's group. Brock and Sydney are the 2 grad students really leading the thrust, which are a bunch of undergrads and many visitors who have come in town. And if you go to the lab in Loomis, you might be, if you're lucky, be able to catch people opening and closing the cryostat, working on the different parts of the instrument. It's really been a big group effort here and a huge amount of work. So it's been really, really cool to see this come along in the last few months. There's also been a bunch of analysis preparation for flight. So Miss Van Kreuk is here at the NCSA as well, working on a simulation suite and our in-flight map maker, as well as thinking a little bit about our calibration strategy. Make sure that we have as successful a flight as possible and can check while we're flying, do we see maps, do we see sources in the sky? So in my mind, this is kind of what we're looking at. We just had our test flight. It was super successful. It has left the team really invigorated going forward. We're working on building up the cryostat. And a lot of this that I've been thinking about personally has been this data analysis pipeline development. So robust calibration, focusing, these data quality checks, and online mapping for during flight, such that we'll be able to enable all of this great science from Tim that I'm really hopeful that we will see in the future. So in my mind, I think this is going to be an amazing data set to start tackling this data analysis challenge. So I'm going to move on to some of the instrumentation that I'm really excited about for going forward with line intensity mapping. So as I told you before, this plot I think captures my hopes for what cosmology can be done with line intensity mapping, this inflation in the history of the early universe, neutrino masses, new light relic particles, dark energy. But to do this, you need to get to the right side of the plot, right? You need to increase your spectrometer hours. And unfortunately, right now we are here at the left side of the plot. This is a state-of-the-art kind of experiment. This is an experiment called time. So time is a grading spectrometer. It's R of 100, 60 spectral channels. And this takes up a volume of something like 700 cubic centimeters. And what I've been really getting interested in recently is these on-chip spectrometers, which are also an R of 100, 65 spectral channel spectrometer, but this is in 0.5 cubic centimeters. And I want you to look at this and think, that seems scalable. That can get you to the right side of that plot. And this is the idea behind the experiment SPT-SLIM, the SPT Shirokoff line intensity mapper. And our idea here is to demonstrate this limb measurement using these on-chip millimeter wave spectrometers, which are this scalable, unique technological advantage in the field. So we deployed a high density 9 pixel dual polarization focal plane. And this is sensitive to 120 to 180 gigahertz here. So looking back at these line intensity mapping plots, that gets you CO at redshift of 0.5 to 2. And we deployed this in November 2024 to the South Pole Telescope. So before I go on, I want to also shout out the other collaborators I have on SPT-SLIM. This is a collaboration with Argonne, Cardiff, Fermilab, CFA, McGill, SLAC, Arizona, and of course at the University of Chicago. So the idea behind SPT-SLIM is you might think SPT, isn't that a CMB experiment? And you're right. So the South Pole Telescope is this 10-meter off-axis Gregorian telescope at Amundsen Scott South Pole Station. And usually how it has been running there for the last many years is the SPT-3G experiment. So if you can imagine like the big 10-meter dish off to the right, usually what happens is light comes in, hits the secondary, hits the tertiary, and then goes into the SPT-3G cryostat. And for one summer, the good folks at SPT let us put in the SPT-SLIM experiment to use the resolution of the big dish, but put in our little baby cryostat and our 2 other optics, pick off the main SPT beam while not disturbing the SPT-3G experiment. So looking a little bit closer at the experiment, at the instrument itself, it's a cryogenic experiment. So we cool it down to 4 Kelvin with a pulse tube cooler, an adiabatic demagnetization refrigerator, an ADR, cools the focal plane to 150 millikelvin. And there you have the detectors at the top. So light comes into the detectors, the radiation is emitted by these feed horns, and then it is absorbed at these antennas at the bottom. So you see like these 2 antennas, you can think of them as like cross dipoles to have polarization sensitivity. And it's read out by what we call a kinetic inductance detector. So light goes down, the power goes down the feed line, isolates one frequency, because remember we need these many frequencies for the line intensity mapping experiment. And it's an inductor and a capacitor forming a resonance. And if you remember from your, Physics 101 class, the reactance of an inductor and a capacitor are in opposite directions as a function of frequency. So what you get is a resonant peak. And this is called a kinetic inductance detector because when light from a photon is absorbed, it breaks a Cooper pair in the superconductor, changing the inductance. And that results in a shifting of the peak. And the shifting of the peak is what we measure out as our scientific signal. And the amount the peak shift tells us how much light there is at a certain spot of sky that the telescope is pointed to. And this is how you get this line intensity mapping measurement. So you can see here the capacitors. This is an actual picture of our focal plane. So the capacitors are in red, the inductors are in blue, and you have these tiny little channelizing filters going all the way down this microstrip line to get off our different frequencies. So here is the SLIM filter bank as a function of frequency. So the first channel here will be able to make a map at 120 gigahertz. The next map here, 120.3 gigahertz. The next channel here, 120.6 gigahertz, all the way down the filter bank until you get to 180 gigahertz. So our data product will be these 65 maps with 18 detectors going into each single frequency map. And instead of just one pixel, we'll have that times 18 to get the whole SPT-SLIM focal plane. And remember, again, these frequencies correspond to different slices in redshift. And what's been really exciting for us is that this is no longer just renderings. This is now real. So we have a real full focal plane that we took down and deployed on the South Pole Telescope last year, or 2 years ago. So we took the focal plane, carried the expensive equipment by hand. The rest of it, we put it into the cargo hold in these crates. We flew from Chicago to New Zealand to McMurdo on the coast and down to the South Pole with the SPT-SLIM experiment. Got our cargo on December 3rd, delivered by tractor. And then we started getting to work. So here you can see the SPT-SLIM cryostat that I showed you in the rendering. There on the right, like the actual real thing. Many, many coaxial cables later, we had the final focal point package there, and there's a picture of the SPT-SLIM deployment team that was at the South Pole at the time. This is a cryogenic experiment, so we took the whole receiver package and slid it into our cryostat. To get something cold, you need many shells going out. So you had 150 millikelvin, 4 Kelvin, 50 Kelvin, 300 Kelvin. And we had a really great cool down there. So our cryogenic performance was basically in agreement with model expectations. So we had an observing efficiency of about 80% with less than 0.1 millikelvin of temperature stability, which is pretty good and what we needed for our science. From there, you want to ask the question, did I in fact build a spectrometer and then did I break it in transit? So we did our band pre-characterization in Chicago with a big FTS before. So you can see from the simulation of our filter bank how that actually turned into the true bands that we see with our experiment. And then when we got to the South Pole, we double checked it with a coarser grain resolution for a transform spectrometer, but it showed that we still have this filter bank quality, still getting these different optical photons. We then lifted SPT-SLIM into the telescope. This was kind of a brutal integration because you had to lift it up outside in the Antarctic cold and then drop it in. So it was a very cold day on the telescope, but thankfully installed with success. And then here's how you can see the optics work. So if you remember from before, I told you that we had this little optics ray tracing diagram to have the light sort of picked off and go in. And here you can see with people for scale, the same optics that then go down into the SPT-SLIM cryostat, which was in this environmental protection down there. We got our first light on January 15th. So this is one of the first times you had on-chip spectrometers actually observing things in space. It's pretty cool. It's an RCW38, which is an H2 region, which is really bright in the millimeter. And you can see how it was observed from 4 different of our pixels. We also took a bunch of other fun data. So for example, we looked at the moon. You might say that we know that's not the most interesting astrophysical target, but for characterizing an instrument, it's actually pretty great. So it's high signals noise, and it's a polarized black body. So if you're trying to ask the question, have I built something that has different frequency response? A polarized black body is actually pretty good for that. So that's sort of the status of SPT-SLIM. We had a deployment with our CO data 2 years ago. We had these first light images, and hopefully next winter, we're going to be able to deploy some more sensitive detectors and do a deeper field survey. We were really limited by cargo delays during our first year. We only had about a week on the telescope, and a lot of it was spent trying to even understand the instrument. Like, how do you tune these detectors? How do you observe under these conditions? What does it mean to have a kid spectrometer camera on the sky? And I feel like we're in a really good place to be able to do a second deployment and get a much deeper field survey for limited intensity mapping. But you may ask me, again, how do we get to these orders of magnitude improvement we need for cosmology? So right now we're here with something like SPT-SLIM, these 10 to the 5 spectrometer hours. And where it gets interesting is where you're in this 10 to the 7 range, because that's about where you start getting competitive with galaxy surveys. And to get there, in my mind, there are these 2 big obvious areas of technological improvement. So the first limiting factor is detector count per focal plane area. This is the spectrometers part of spectrometers out, where you can pack more spectrometers in. So if you want more detectors per focal plane area, you either need to build a bigger telescope, which is obviously super expensive, or get more clever about the way that you're packing your detectors into your current telescope. So SPT-SLIM, as conceived right now, has one sort of fundamental non-ideality, which is that the actual only, it's manufactured in this planar sense, and the only part that needs to see light is these pixels in the center. These filter banks aren't optical elements, and in fact, we put a lot of effort into making sure that no stray light gets absorbed on them. So it's as if you're missing all of that light at the edges because those don't need to see the sky. So we've been thinking about these architectures where maybe you could take the wafers and rotate them vertically and be able to have the spectrometer on these cards instead and get all of that focal plane area back. The second big limiting factor is dielectric loss. So when light comes into our OMT and then goes down the feed line, ideally the light gets channelized off at the different frequencies for the different redshifts. But unfortunately, you're making this out of real materials, not just completely in vacuum. So you have this exponential decay as you move down the feed line. This is called the dielectric loss. And what we've been recently thinking about is this project that we call LIMS, which is leveraging advancements in nanotechnology for cosmology experiments, which is a partnership between myself and Maz Ali at TU Delft. And the goal here is to try to test new dielectrics. This is very material science question for these next generation cosmology instruments using materials that our colleagues actually developed for quantum transduction. So they went ahead and fabricated a bunch of different dielectrics. So there's silicon carbide that they are world leaders in, and silicon nitride, which is more standard from what we've been doing for SPT-SLIM, using our cosmology detector test structures. And here you can see some close SEM images of these resonances, which have this very nice adhesion at the edges. And then at the KICP at Chicago, we've have these custom cryogenic setups and analysis pipelines to actually go through and test all these different dielectric materials. So these are the measurements we make. We basically take the resonators, which you can see at the top, 4 of them, and we sweep them for temperature and see how their responsivity changes to the function of temperature. And from that, we can get our loss measurement. What we're trying to do here is get to the bottom left corner of this plot. So on the y-axis is loss, and on the x-axis is deposition temperature. So the colder you deposit, the more you can use different materials, because it's really important that once you deposit one layer of your detector stack, you put the dielectric down, you do another one, you can't melt the first layer of the detector when you deposit the dielectric. So a lot of these hotter deposition temperatures limit what kinds of architectures you can use and what kinds of metals you can use. So trying to do this reliably, turning the knobs in a systematic way and slowly moving down to the bottom and left side of this plot has been something that we've been thinking about at University of Chicago. So this, I think, is just the start for on-chip spectrometers. We had SPT-SLIM, we had our first deployment, we're hopefully looking at a second deployment. And then I'm hoping that with some of these material science things that we're developing, we'll be able to make a next generation CO focal plane that'll be much more sensitive than the current generation of ones. So with that, I'm going to move on to my final topic of this presentation, which is asking, with line intensity mapping, how do we look as far back in time as possible? So when I spoke with you earlier about my hopes for line intensity mapping, emission from atomic and molecular spectral lines, you actually should think about them in 2 categories. So there's hydrogen and then there's everything else. So you can only get these things that have carbon in them after the first supernovae happen. And before that, you're really just looking at hydrogen. That's the only thing that was really around before first stars that has these lines. So when you think about the early universe, there's really 2 types of photons. There are CMB photons, and there are these hydrogen photons from the spin flip transition of hydrogen. So hydrogen atoms undergo this spin flip transition. This emits a photon at 1,420 megahertz, which is 21 centimeters in wavelength. So if you've heard of 21 centimeter cosmology, this is what this is referring to. So you're talking about the 21 centimeter signal. You're asking about something that is proportionate to 1 minus the ratio of the temperature to CMB photons versus the spin temperature of hydrogen. And the thing that's cool is if you make a plot of that, you get all of this really rich structure that can tell you about what was happening in the early universe. So I'm going to walk you through why there are wiggles in this plot. So bear with me. So right at the beginning, the universe was really, really dense. So Compton scattering keeps the kinetic temperature of the gas in equilibrium with the CMB photons, and sets the spin temperature to be equal to the CMB. So if you look at that ratio, if those 2 things are equal, that gives you 0. And that's why we start at 0 on the left side of this plot. We're keeping track of a few things, the temperature of the CMB, the kinetic temperature of the hydrogen, and the spin temperature of the hydrogen, and asking what does that mean in terms of the y-axis of this plot. But the universe is expanding and cooling. So the gas then eventually thermally decouples from the CMB, but it cools adiabatically faster than the radiation field. So hydrogen cools as 1 plus z squared, whereas radiation cools as 1 plus z. And collisions couple the spin temperatures to the polar gas. So this neutral hydrogen absorbs CMB photons and causes this absorption dip here. But then, as the universe is still expanding, it gets a little bit less dense, and the gas is no longer dense enough for these frequent collisions. So TS returns to being dominated by the radiation cooling from the CMB photons, and you get out of this dip and it goes back up again. But if you remember on this far left side on this plot, things start happening in the universe. So you start having the first stars. They are getting these Lyman alpha photons. And then suddenly there's all these Lyman alpha photons going around, such that TS is now again coupled to the kinetic temperature. But the kinetic temperature has still been doing this expanding 1 plus z squared thing as it has before. So it is even colder than before. So you get an even deeper dip. But because you have these first stars, there is so much other stuff going on. You start getting this X-ray heating of the IgM, and this starts heating up the gas. You get this much, much hotter TK, and then you come out of this dip. And at the end, the IgM is ionized, there's no neutral hydrogen, signal becomes 0. So this is this 21 centimeter signal. It's telling you about what is going on in the early universe. And the cool thing about this as a probe is that if you can detect this, this is a direct probe of the expansion history of the universe, the formation of the first stars and galaxies, and both the depth and the width and the location of it encode cosmological information. Yeah, so let's go. Let's make this measurement. Why is this hard? And the answer is 2 parts. One is RFI, and the other is the ionosphere, actually. So when you think about the ionosphere, you might think about ham radio enthusiasts, and people with ham radios can talk to people on all the other side of the world because they can bounce the radio waves off the ionosphere. And that is great if you're enthusiastic about ham radio, and it is terrible if you're enthusiastic about cosmology. Because if the radio waves are bouncing off the ionosphere, that means nothing's permeating into space, or conversely, no astrophysical signals are getting in through the ionosphere. And the frequency, you can keep doing this up to higher and higher and higher frequencies until at some point your ham radio signal escapes into space. We call this the ionosphere cutoff. And different places on Earth have different ionosphere cutoffs. So I was looking at ionoson data, making histograms of number of days and the highest frequency recorded by a reflection. So you want this number to be really low, because so for example, in Gilson, Alaska, this is the orange line on this plot. So this is getting you most of that 21 centimeter dip. But somewhere like Boulder, Colorado, like the instrument is only sensitive up to 10 megahertz, you're clearly getting some peak over here as well. And then you're starting to get into the point of this dip that you want to be detecting for your cosmology experiment. But there's a cool trick. And you might ask, like, on this plot, well, why are Alaska and Antarctica so much better than like Wallops Island or Boulder, Colorado? And it's because there's this feature called the ionospheric trench around the North Pole and sort of the South Pole, and it has to do with the alignment of the Earth's magnetic fields. And those are places on Earth where the ionosphere is actually super, super thin. So some of us at Chicago have decided to go out and try to measure whether you can make this measurement from one of these locations. So we have this experiment that we called the Dark Ages experiment. The working title is The Bears. I don't know what we'll really call this, but we've been running with it to the point that I'm now giving this title in a talk. So I guess it's kind of real. Yes.
So if you're from Chicago, if you go back to your ionospheric trench,
Yes.
that does seem to go very close to us, though, where we are here.
To Chicago, I think this is mostly Canada here. Like this is cutting through Alaska right there. I think Chicago would be
A little low.
a little bit lower, but we
Yeah.
will, yes, deploy this experiment on the roof of the physics building in Chicago first. So I will let you know at the end. So this is a collaboration myself and Abby Vera, Cosmin and Eric at U Chicago, and then grad student Michael Hettu and undergrad Amelia Rebound. So we're doing a Pathfinder in fall 2026 for the ionosphere and RFI in this low ionospheric cutoff region in Tuluc, Alaska, which is right here up in the north of Alaska. And we basically chose this location for 2 reasons. So this is our site survey. We chose it because there is a road, so we can drive there. But it's a very remote road. So we have all these sites where we're going to take sleds and go over these mountain ranges And yeah, I've been like walking on the Stairmaster, like preparing myself for this like negative 20 degrees sled adventure. So it's over these slight ridges, as you can see in the topological map, where hopefully we're out of the viewshed of RFI, close enough to the road that it's not going to be completely miserable to deploy, but away from things where you can see like Met Towers, Tulip Station, etc. Yes.
And this is summer?
We're gonna be putting it, you want the long nights for the ionosphere, because the ionosphere is much better in the night. So we're gonna go in like November, when you get some hours of daylight for us to trek our sleds, and then we can leave the experiment there overnight and see what we get during the nighttime versus the daytime for the ionosphere. So this is the instrumentation motivation. It's just these simple off-the-shelf parts to characterize the RF environment and the ionosphere cutoff. With a more custom array to follow, we feel that this is going to actually pay off the site. So it's just an antenna with a Raspberry Pi, a GPS receiver, a spectrum analyzer, and some calibration board where we can switch between a noise source, a calibration source, and our receiver. And this has been put together by grad student Michael Ettu at Chicago. And I'm really hopeful that we'll be able to take this to a field station and see whether this is actually a viable place to do this 21 centimeter cosmology. So that sort of brings me to how I'm hoping and thinking about tackling these big challenges for line intensity mapping. Because what my big dream is that line intensity mapping becomes the new CMB. That we could do a wide survey in the Atacama Desert to constrain dark energy equation of state, the Hubble constant, and inflation with PNG. We could do a deep survey near the South Pole, constrain the matter power spectrum, galaxy bias, and galaxy formation evolution. Maybe even possibly a LIM space mission to gain sensitivity to lines you can't access from the ground and remove atmospheric contamination. So I'll leave you with my final slide, which is just timeline. We just deployed SPT-SLIM. We're looking forward to potentially a next generation CO LIM focal plane that will deploy to the South Pole again for another go in the next few years. Tim is going to fly soon. That's really exciting, especially around here in Illinois. If you haven't seen it yet, I would encourage you to go up to the fourth floor of Loomis, check out the cryosat, talk to the grad students and the faculty members working on this. It's really, really cool and exciting to have it, especially having it here. And then maybe we'll be able to do a future 21 centimeter dark energies array from the Alaskan tundra. So I hope that some of this timeline captures the hope that I have. I hope that you guys are excited about this too. And with that, I'll take any questions.
So 121 slides and no bingo, right?
Yeah, no.
I got it. All right, any questions? I have a quick question. Well, Brian has a question.
Yeah, so I was wondering what kind of spatial resolution you'll get. So you mentioned the angular scales and redshift ranges. What does that correspond to in sort of your resolution and the plane of the sky and the line of sight, like how megaparsecs? Yeah.
Oh, the whole shtick of line intensity mapping is that you don't need really good angular resolution because you're just capturing all this integrated emission. So one of the sort of perks of this is that you don't need a telescope like ALMA to actually make these measurements. So we're looking at dishes like the SPT, for example, is total overkill for this kind of a thing. We used it because it was a platform that we could deploy on. You don't need a 10-meter mirror. You really need something more like a 2 or 3 meter mirror to do this with a millimeter wave. So the resolution right now is really not the thrust of this experiment.
So my quick question was, SPT-SLIM, you had a bunch of different frequencies that you're measuring, and you showed how there was sort of this dielectric decay between different frequencies. So what sets the number of frequencies that is optimal for this kind of experiment?
Yeah, so it depends on how fast you think the universe is changing as a function of time. Of course, if you have more frequency bands, you can synthesize them into thicker chunks. So there's an instrumentation reason that's setting the resolution of these spectrometers, and that's basically how many peaks you can crunch in without getting crosstalk in the peaks next to each other on these on-chip spectrometers. And that's set by how well you think you control the scatter in the nanofabrication process and the dielectric constant, which really relates to the quality factor of the resonators, like whether they're sharper peaks or wider peaks.
And is a cosmological probe more is better?
Not necessarily. So doing like an R of 100, R of 200 spectrometer should be like pretty much fine.
Any other questions?
Yeah, I was curious about kind of the next generation of SPT-SLIM and kind of the next district town to use that. Do you have a sense for what kind of targets you want to look at? Is it going to more like extra sources, nearby stuff, calibrate, or starting to do these kind of larger fields?
Yeah, so the hope with like line intensity mapping is that you're doing these field surveys. And technically speaking, it shouldn't matter where you look because, you know, space should be the same in every direction. We of course have been also looking at these, bright millimeter wave sources just to like see, are we seeing the black body? So like RCW 38, for example, you're seeing these curves that show their like continuum emission. And maybe you could imagine that if you have sensitivity to lower redshift things, you could see lines in sources at redshift 0.
You have a question?
Thanks for the talk. So I was curious for the bears, are you worried about like wildlife?
I've never had to deal with before as an Antarctica scientist. So in Antarctica, there's like some penguins in McMurdo, but we have a balloon, so there's no penguins on the balloon, right? And then at the South Pole, there is no wildlife. So we've been thinking a decent amount about how you wildlife proof these instruments. And the idea is that you put your electronics in sealed boxes, basically. And if you don't have any cables, that could be nibbled. So you put shielding on your cables such that animals can't shoot through them. But this is this is a new one for me. This is a new one for me. And good point, we have been thinking about this.
Okay, we'll do maybe Ethel and Emma and Rebecca. So we'll start with Emma.
Okay, I was curious, so you talked a lot about how if you have more spectra time, you can get better precision. Do you have like a vision for like a DESI like instrument that, I don't know, it takes a lot of spectra at once? Like I know you talked about how SPT-SLIM was like you kind of, you added this little piece to the existing SPT instrument. So like, can you envision doing that with something else like DESI?
Yeah, so with our instrument, every pixel is getting the whole spectrum at once. So it's not that we need a bunch more little cameras to look at different spectrum sources. We're doing a field map and then getting the whole spectral cube of that by scanning across the sky. And the hope would be, like you say, like what is the next scale? You would hope to fill like a whole focal plane of something like a full CMB telescope with these kind of spectrometers, something like ACT or the South Pole Telescope. These could be drop-in replacements because it's the same frequency band. And that would hopefully be the goal.
Yes.
Okay, so there are plans to install like a radio telescope array on the moon, I think, to
Yes.
detect the
Lucy Knight.
1 centimeter line.
Yes.
So if this plan was realized, what sort of like questions can we answer that we couldn't have without like a lunar-based array?
Yeah, so this is going after the same science as these lunar-based experiments. As far as I know, all of the funded lunar-based experiments will not have the sensitivity to detect the cosmological 21 centimeter signal. And our hope is that, instead of having to go through all of the rigmarole of going to the moon, you can just see if the ionosphere is good enough on Earth and wait a little bit longer. So we're doing this site characterization to basically see how much longer would you have to wait to do an Earth-based experiment as opposed to a moon-based one, which has a huge advantage of being able to like make new instruments, build it there, set it up yourself, instead of having to require all on deployments of spacecraft.
So there's a lot of existing high-redshift H1 cosmology, say with EOR arrays, the projects, the square kilometer array
Yes.
patterns and so on. So how does your H1 project compare with that?
Lower frequency. They're going for the, it's just much lower frequency than like Hera or Chime or SKA or any of these higher frequency ones.
One last question from the people.
Yes, coincidentally, today in the Atlantic, there was an article about the HARPS array.
Yeah. We're trying to be far away from them.
Yeah. Is that, do those experiments pose any kind of threat to your, because they'll heat locally the ionosphere in some places and that might change the cutoff frequency.
Yeah, so we've thought about taking our experiment and putting it underneath and using that to like calibrate the beam response. We hopefully are just going far away from HARP, which is again in Alaska as well. We thought about, we take the thing, put it underneath, see what that looks like. Because obviously what I would like to have is like HARP right next to my experiment.
Yeah.
And set up a calibration pulse every once in a while if it wouldn't like blow out my amplifiers. And use that as some kind of calibration signal, but I assume they would not want to operate in that way.
Yeah, I think they're a lot closer to Anchorage, so.
Yes, exactly.
So let's thank our speaker again.
I have a very short question. Did you put the dog in the?
No, I didn't.
Oh, okay.
So, Jessica is going to catch a train at 7, but we ended a little bit earlier than normal, so there might be enough time for dinner.
Yeah.
Who's interested, so go